Welcome to the 7th unit of the module we are discussing, that is on the control circuitry of the computer. So, this is the 7th unit in which we are going to study about microinstructions and microprogram. Basically, in the last unit we had seen that basically how to generate the control signals if the hardware for this is exactly fabricated as a hard coded non modifiable circuit, which you actually call as the hardware control unit. That is the sequence of micro instructions, and the control signals to be generated corresponding to that can be generated using a hard coded circuit which is synthesized from its finite state machine control. So, that part we have seen that the circuit which generates out of this is a non-flexible circuit, but it is very fast, but it is non-flexible and it cannot be changed. In fact, for a given sequence of micro instructions and the control signals correspondingly, we generate a finite state machine and then we synthesize the circuit out of it. In the next 2 units basically, that is on microprogram control, that is these 2 units. So, basically we are going to study how the same thing, that is generation of the control signals, can be done in a more flexible way and in a terms of a program. So, it is not, it is very similar to what we understand by a normal computer program, which you have already looking throughout these lectures. But it is, instead of the macro instructions, we will be using micro instructions, and that controller we will actually call microprogram based control. So, this actually unit is focused on the generating of the control signals using a microprogrammed approach, which is more flexible, you can change it, but of course, it will be slower than a hardware circuit. So, what is the unit summary? What we are going to look into that? Basically, if the control signals are generated from a dedicated circuit, we call it as a hardware control. An alternative approach is basically which we can generate such signals which are basically programmed into some kind of a memory. So, if it is a memory based logic in which each of the memory cells or each of the memory word has the corresponding control signals to be generated, then that approach is actually called the microprogram control unit, which is basically we are going to study in this unit. So, basically a microprogram consists of a sequence of instructions, and basically these instructions are nothing but which are the basically a microprogram is corresponding to a basically a sequence of micro operations, that is very well known, that a macro instruction has some micro instructions which we have already discussed few lectures back, and corresponding to each of the micro instructions or the micro operations, basically we have some of the control signals, like for example PC in should be equal to 1, etc. So, those bits we can actually make them 1, and whichever are not required we make them 0 and store in one word of a microprogram control memory. So, microprogram control memory is very similar to a normal memory, but we allocate it separately for the microprogramming based control. So, we call it as a microprogram memory. So, if we can put these control signals explicitly in some memory locations, then when you access that word of the memory, such the corresponding control signals will become 1 and 0 as required. So, that is basically the idea of a microprogram based control. For each of the micro instructions and the control signals that has to be made 1 and 0, you directly write into one word of the memory, and then step by step you actually go from one location to another and so forth. So, basically a microprogram control unit is a simple logical circuit. In fact, it is a memory with some peripheral circuits which actually will go through sequence of micro instructions. In fact, there is nothing but 0 1 0 1 1, these are some of the control bits or which have to be made 0 and 1 based on the instruction, micro instruction. They are written in a memory, and when you access that memory, those values will be given as directly output as control signals. And therefore, you have to go in sequence, that is one job of that logic, and then basically sequence, I will tell you what is sequencing and control signal generation. It has 2 parts basically, that is this control signals has to be generated in sequence. So, control signal generation of the control signal is very simple, that is just these values has to be dumped from the memory and it has to go to the corresponding locations. So, in this case generating the signals is very straightforward, unlike in a hardware based control where you have a finite state machine and the corresponding Moore and Mealy machine logic has to be implemented. Here it is very straightforward, the values are already in the memory and you dump it out. Sequencing actually is slightly tricky, which is somewhat very easy in a finite state machine approach, because there you have the flow of states which can take care very easily, but in this case sequencing is slightly tricky, because unless otherwise specified you will go from step 1 to step 2 to step 3, that is the sequential memory locations, microprogram memory locations like step 1, step 2 and step 3 and so forth. But whenever there is a jump instruction and you require also to check some flag conditions, which is simpler in finite state machine based approach, but here we have to have separate arrangement, so that just by looking at the control signals, that is the input output signals, then you have to also look at the flag signals, then you decide that whether the next location is the location which has to generate the corresponding signals, or you have to jump to some other location where the control signals has to be generated accordingly. So basically microprogram based control is very simple. Whatever signals you require, you directly put them in the memory location. So whenever you have to generate those control signals, that memory word has to be fetched. But only sophistication is that you, in normal case, you will move through step 1, step 2, step 3 like that in the memory control memory sequentially, but whenever you have to jump, you have to go to some other corresponding memory location. So accordingly the program counter, we call it actually here microprogram control counter, because the architecture is very similar to that of a normal program execution. So whenever you have to jump to others, slightly more sophisticated program mechanism has to be used, which will take the values from the input output signals as well as the flag signals and take decision accordingly. So there is a slight difficulty compared to the hardware control, but simplicity here in terms of, if you compare to hardware control, is that generating signals is very simple. There is no circuit explicitly required. Required values are stored in memory locations which are directly fetched and the values given. That is what we are going to see in details. Basically, we can also say that microprogram is very similar to a computer program. In case of a computer program, the whole macro instructions are stored in a memory, and you just actually fetch it one by another, and whenever you require a jump instruction, you jump. That is actually controlled by the program counter. Here also it is very simple, very similar. Basically, instead of a program counter, we call it as a microprogram counter, and also you have a explicit memory which will actually store this control signals corresponding to each of the micro instruction, and that is actually called the microprogram memory. So there is slight architecture is more or less similar, but before the term, because the flow of instructions which happens in a normal macro program is very similar in a microprogram, but we use the word microprogram to differentiate basically. Similarly, it has both conditional and unconditional branching, so all these are very similar. So that is what we are going to look in this unit. So what are the basic objectives which you are going to fulfill after doing this lecture? So first is a comprehensive objective, in which case you will be able to explain the concept of micro instructions and the microprogram of an instruction. That is, given an instruction, you will be able to explain that what are the micro instructions corresponding to that. In fact, you have already learned it in the some classes back, but in this case also you will be able to translate it into a microprogram. Then next is an analysis objective. You will be able to categorize the control signals in different groups and the format of micro instructions. That is, given some instructions, macro instructions, you will be able to generate the micro instructions and the microprograms out of it. Synthesis, next is the synthesis objective. Construction of, or you will be able to construct basic components of a microprogram control unit and its organization. That is, you will be able to synthesize a whole microprogram control unit given a set of instructions. So these are the basic objectives of this unit. Let us go into the unit in details. So what is a microprogram control unit? So already we have seen that in our finite state main machine approach, or the hardware based approach, basically we have some states which are synthesized as a hardware. So you cannot change them, but it is quite fast. That is the advantage. But problem is that for a given macro instructions, or sorry, a macro instructions or a set of instructions, this flow is very much fixed, that cannot be changed. So to have a more flexible approach, we actually go for something called a microprogram based approach. So let us assume that it generates some signals called 1011. Maybe the first signal is for program PC in, second maybe for PC out, this may be for MDR in, maybe some control signal values. Maybe this state generates 1011, next state maybe 1000, next state maybe all 1, some arbitrary values it is generating. So in this case, you just move from state 1 to state 3, and maybe on some other condition check you can very easily implement. It can go to some other state where you have all zeros. So we can have some condition checks over here based on the inputs and the flag. But in case of microcontrol, so in case of hardware control, there are some, it's a Moore or a milli machine, there are hardware circuits which will actually generate these values based on the state variables or the state encoding process. But in case of microprogram, we actually store these values called 1011, 1000, 1111 and all zeros in some memory location, that we are calling as the microprogram memory. Then we go from this step to this step, this step to step, and this step to this step, sequentially using a microprogram counter. So in microprogrammed architecture, if you store these values in a microprogram memory, then it is very simple. Just you go from one memory location to another, fetch the values, and automatically control signals are generated. But what is difficult in a microprogram approach compared to a hardware approach is that, for example, going from here to here or here, maybe depending on some input values or a flag value is simple, because it is a hardware circuit which is implemented. But in this case it is a memory which actually goes here. So either you go from here to here or you go from this location to this location. For that basically you should have some sophisticated arrangement, which we will see, which is not very straightforward, which will have to have some more arrangement, so that depending on some kind of input values you decide whether this is the next instruction or this is the next instruction. So for microprogram control unit, when you are implementing a branch kind of an instruction or where conditions has to be checked, we have a slightly round arrangement, but it is straightforward in finite state machine. But overall microprogram is very flexible, because you can easily change the code if you like based on the requirements, but the sequencing is slightly tricky, which is more difficult in case of your microprogram. Jump instructions based on some condition check is slightly sophisticated compared to a finite state machine. So basically that is what is a microprogram control unit. So basically as I told you, the microprogram consists of a sequence of instructions in a microprogramming language, that is correspond to a microinstruction. Macroinstruction, there are some microinstructions, and basically you have to sequence through the microinstructions and generate control signals to execute. So that is the two jobs, that is, say for example, like as I told you, say these are the signals which has to be generated. So sequencing through the microinstruction is, or generating the control signals means if you read this memory location, so these values will be coming out from the memory, microprogram memory, so that will set the values accordingly. So generating the control signal for each micro instruction is simple, just fetch the memory location. Sequencing means I will generally sequence like this, but whenever there is some jump instruction you have to follow, or you have to move from one instruction to another based on, which is non-sequential, based on some input variables, then somehow I have to change the value of microprogram counter, which will not be 1, but it will go to some other location. So in that case sequencing is slightly more sophisticated. Again, as I told you, the microprogram concept is very similar to a normal program. So normal programs basically have some instruction which is fetched, decoded, it goes to an instruction register, and it happens in that way. But same thing happens here, but like in a macro instruction you have an opcode, then you have operands and so forth. But here there is no questions of any opcode and operand basically. So what happens, I will just tell you an example. Maybe say we have the instruction called add R1, R2. So this is a macro instruction. So in that case you will have the, when it goes to the instruction register, you have the opcode and you have the operands. But in case of a microprogram, basically you have some bits and bytes. So in fact these are also bits, it was in terms of bits, but here we have opcode and operands and have separate meanings of different fields. But in this case what happens, generally there is one set of fields which will just correspond to the control signals directly. That is, you will directly feed these to different control positions like program counter in, ALU to be added, etc. That is slight difference, but the control flow is very similar. You go from one instruction to another, then to another, if required you jump. But basically also is a program counter which will take care of this. But that concept remains same, but here you need not decode like whether it is corresponding to add or store or something like that. Directly control signals are generated in a microprogram. But the flow architecture is same, so therefore we call it, there is a microprogram PC, that is program counter basically, and also this memory we call it as a microprogram memory to slightly differentiate. Flow is same, but only the purpose is bit different. So in case of a normal macro program, you have add, store, load, such instructions are executed, you have an opcode and different operands. So you have to use this opcode, go to an address instruction decoder, and from there you will be able to generate some kind of control signals. But in case of microprogram, the control signals are actually basically are provided in the instructions itself, because macro instructions actually get translated into micro instructions and they actually are encoded in terms of control signals. Okay. So basically the microprogram control unit ensures that the signal will be generated in correct sequence. So sequencing here is a bit tricky, because generating control signals is directly they are encoded, directly they are actually put in the memory location. So if you just take cell 1, memory row 1, memory row 2, memory 3, automatically control signals are generated as default because they are already stored in the memory. Sequencing is actually very important here, because many times we will depend on the condition codes and status flags based on some storage, that is some signal from the memory, that is WFMC, based on some case like some interrupt, etc., because of some case, and also some status flag like 0 flag, carry flag. So all these things must take into picture, and then you have to decide whether it will be the next phase or it will go to some other instruction which is not consecutively. So you have to have also arrangement for something called a branch decision. So in like normal programs, we have micro instructions where actually it is conditional, and also you have something which is unconditional. In conditional, it is required to specify the address of the microprogram memory where the control must direct. So it means if it is some condition is not true, you go here, that is the next step. But if it is true, you go from here to here, but then you have to actually tell what is the address. So that part is quite obvious, but in this case you have to tell the address of the microprogram memory. Of course, that is because that is true because you are executing in a microprogram memory. So microprogram memory architecture and normal memory architecture is not much different, they are almost the same thing, but we are allocating some part of the microprogram memory where you have the microprograms or the micro instructions corresponding to the macro instructions. We will take with examples, then it will be more easy. Like for example, if you have some instructions called add, R1, R2. So first phase is called the fetcher instruction. So we have discussed many times that for most of the instruction, fetch phase is similar. So whenever an instruction has to be fetched, the sequence of micro instructions is always similar. So whenever an instruction has to be fetched, you can directly invoke that part of the memory, microprogram memory, which has the micro instructions corresponding to fetch. After that, the add will be decoded, and then different types of activities has to take place. So whenever add has been decoded, then it is a register to register operation. Then the instruction or the micro instructions which is stored in the microprogram memory corresponding to add, register to register, that will be invoked. So that series of micro instructions will execute, which will actually execute add, which is from register to register operation, and then it goes forth. So we will take some examples when it will be more clear. For the time being, just take the fact that instruction fetch, decode and execute. So fetch, everything is similar. So whenever a new instruction has to be fetched, a fixed block of micro instruction which corresponds to memory fetch will be invoked. Invoked means microprogram counter will start pointing to the first instruction, micro instruction, which corresponds to instruction fetch. Then when an instruction fetch is done, then we are decoding in the instruction register, and then accordingly it will tell that it is a add instruction which is from register R1 to R2, that is basically a register to register instruction. So corresponding micro instruction, corresponding MPC will start point to the microprogram address or microprogram memory address where you have the microprogram corresponding to add R1, R2. When it will end, again other steps will follow. So that is what has been actually is the job of a microprogram control unit. So apart from branch address, these microprograms can specify which state flags, conditions, etc. has to be taken for the condition check. So that means in a very nutshell, basically you just microprogram counter increases one by one, but whenever there is a condition which depends on the inputs, depends on the flags, depends on some IO input which you get it from some IO device, then all these conditions has to be checked, and then the microprogram control sequence will tell the microprogram program counter that whether it is the next or whether you have to go to some other memory location of the microprogram, and then you have to tell exactly which location to go. So that part has to be a part of the sequencing circuit logic for microprogram control. Okay, so what I was saying, you can just read in this slide. Basically, we have every instruction has two parts called fetch and execution phase. Execution phase means here I am telling that decode, do the operation and store. So basically, for all instruction fetch phases is similar. So whenever a new instruction has to be executed, first actually the microprogram corresponding to fetch will be executed. So the microprogram is stored in a specific location in the microprogram, and execution starts from that memory location. Maybe we have this is a microprogram memory, maybe this part is reserved for the instructions, micro instructions corresponding to fetch. So whenever a new instruction has come, your MPC will point to this. So whenever this instruction is completed, that is 3 or 4 micro instructions for fetch is completed, then again the MPC will start pointing to some XYZ position. So it will come here and it will end and it will now be floating. Now the instruction decoder, basically that is the instruction decoder, will have the instruction like add R1, R2, store or something, then it will decode and find out what is the instruction it corresponds to. Maybe it is a load instruction, then again accordingly the microprogram counter will start pointing to that location in the microprogram, which is the first instruction, micro instructions correspond to that particular instruction. If it is add R1 and R2, so this one corresponds to the micro instruction starts, where the micro instruction starts, which corresponds to add register to register. If it is a store, so it may be pointing to some other location in the microprogram which corresponds to the start address of the microprogram, which corresponds to load or store. So basically this is how it actually happens. That is, for any instruction, the first phase is similar, that is the fetch, and then after that, based on the instruction type which is decided by the instruction register, it will take the MPC value to corresponding position in the microprogram memory where the microprogram corresponds to that instruction sits. So now if you look at this slide, it actually tells in more formal manner, which I was saying, that during the execution of a microprogram control, the MPC is always incremented. So it goes accepting the branch condition. This is very obvious that whenever there is a branch, it will go to other place, but two other cases basically it does not always increment. When an end instruction is encountered. So what is an end instruction basically? Say for example, as I told you, fetch is a default, it means sequence of the default sequence that has to be executed whenever any instruction has to be taken from the memory and executed. So whenever an instruction is there which has to be executed, basically it pass the microprogram corresponding to fetch is MPC points to that part, and whenever the fetch instruction set is micro instructions are over, or you go to an end of a microprogram, then actually then it does not go ahead, obviously, because maybe these 3 micro instructions are required for fetch. So after that, this part actually ends for that micro instruction. So whenever it ends, then it has to again wait. Whenever it sees an end instruction, it does not go. That is obvious. Basically, if you take an instruction like add R1 and R2, so that is a macro instruction. It will have many small micro instructions programs for that. Like fetch will comprise for one microprogram. Then add R1 and R2. After decoded, it is executed. That is R1 and R2 have to be executed and it has to be written in R1. So basically that part will comprise of the second micro instruction program. So basically when the fetch is over, it will go to the end instruction of the microprogram, and of course MPC will not increment. It will be blank. Then basically that MPC will now start pointing to the next instruction basically which corresponds to that macro program. Like for example, it is add R1 R2, it will start pointing. So whenever it reaches the end of one micro instruction program, so it will again MPC will not be incremented, it will be waiting for the corresponding off code, that is the instruction register will tell basically where it has to point, it corresponds to the particular instruction. So at that time it is not incremented, it waits. Basically when there is a jump instruction, of course the condition will tell you that where you have to jump. So at the end of the microprogram, the MPC is there with the starting address of the microprogram for the instruction which is presently in the IR. So basically these are the two cases, this is case 1 and basically this is case 2 when we do not increment. For all other cases basically you increment the program counter. One condition is branch, that is obvious, and another condition is basically for a given instruction, for a given instruction is implemented by 2 or multiple microprograms. So whenever one microprogram is over, then you have to wait for the other, and that one will be told that when one microprogram phase is over, which is the next microprogram to be executed, that will be told by the instruction register. Like if it is add R1 R2, the execution will start from a different part. If it is load R1 R2, then it will be a different way. So based on different instructions, basically what are the execution part, that is going to tell you which microprogram has to be executed for that. So in these two cases basically the program counter has to be loaded, one by the branch case and one by the instruction register. So basically this is what in a nutshell we have seen. For a given program, macro code, there is a sequence of microprograms. Like for example, if I take a macro instruction like add R1 R2, it will have corresponding different microprograms which will execute it, and the microprograms actually exists in different parts of a microprogram memory. So basically what our job is to do, you have to actually generate these control signals and you have to generate the address of the control memory in the next step. That is, you have to do the sequencing. That is what are the jobs. So now we will see how basically a microprogram is organized which has to do these things. One is the control signal generation and second is how you can do the proper sequencing. In this case, again repeating, control signal generation is very simple because you have a memory, and in all the memory bits you store the required signals which has to be made 0 and 1. So Basically, so whatever I was telling you can read in this slide. Basically, if there is branch, then there are two cases in which you cannot go sequentially when one microprogram ends, and in what case there is a branch instruction. So in this case, basically you have to think of the which actually next address to go, otherwise MPC is just incremented. So basically, so now if you think basically this will be your program, microprogram. So basically the microprogram is nothing but there are some parts of a memory. So I am filling the value 0, 1, 1, 0, something like this has been filled up. Now I have to reserve some part here and some part. I will tell you why these things have to be reserved, because otherwise it will go in sequence. It will keep on going in sequence one after the other, first this location, this location, this location, and so forth. Now somehow say that if I want to say that I want to go from this memory location to this memory location, that value, that is, this is the present state, next state I have to go not this but this, some other memory location. So some part of the memory here will be telling that what is the next phase, that is the address. That is the address of the next location which the microprogram has to go, if some condition is satisfied. So another part you have to keep for some conditional variable, that is based on some conditional variables. Maybe these are the variables which has to be checked. Means I am just telling you the basic gist. In a few slides we will see the more concretely how this is to be designed. So basically this one will go in this manner, but and these are basically nothing but your control signals 0, 1, 1, 0 and 1, 1. Some part of the memory I will reserve at the next address register. If I say that it may be XX or 00 or something, then it will tell that I have to default go to the next instruction. But if I say that some values are there, maybe 1011, some decoding is there which will tell maybe 101. That means it will tell that the next instruction is not this one, but it has to go to 101 if some condition based on this memory location holds. Maybe if you say that 00, it tells that no condition has to be checked, it will directly go to 10, that is default jump to memory location 11. But sometimes if you may say that 01 and 101, and this 01 may correspond to saying that basically the carry flag should be 1. So if the carry flag is 1, then you jump to 101, else you increment. So this is the way a microprogram memory will look like. You will have one part which is the most important part of it, that is the control signal. Some part you have to reserve for the conditions which you have to check. You can say 00 or XX, that means no condition has to be checked, and you can also say XX, that means no condition has to be checked, nothing, you just increment. But if I put some values over here, it may mean that that condition if it holds, then only this condition, this is the memory location we have to jump, or you have, if it does not hold, you again go over here. So basically apart from this control, you should also have to store where should be the next memory location and what should be the condition. So as this is not a finite state machine, so in case of a finite state machine, basically you can have some conditions and the sequencing actually is maintained, like if this is the case you go over, and if this is the case you go over. So these condition checks are put in these transitions, and this destination and this destination are denoted by the states. So here we do not have any kind of a state structure. So one part of the memory we reserve for checking the conditions, and another part of the memory we say that do you want to go over here or do you want to go over here. So that basically if you want to go over here, it is default the next, but this may not be the next instruction. So to go to that state, so location of this also has to be stored in the memory. So to match this condition and the jump address to this, we have basically the memory has three parts. This is for your control signals, this is maybe for your next address, and this part for your check of the condition. So the memory has to be basically divided. So that is, if the present instruction requires a jump, then the address of the jump in the memory location is stored in the branch address field. That is what I was saying. Basically that means this is the whole instruction. So if you have to jump, so this is going to be your address where it has to jump, but that is this part is actually called the branch address field. So therefore you have to explicitly mention in the instruction itself that if some condition is true, you have to go to this address. If the condition is not required or you need not jump from this instruction by any means, you can put it some default variable. If the jump unconditional, this is actually called the condition select field. This is actually called the condition select field. Of course, because the jump etc. will happen based on some condition. So as I told you, you can have different encodings, that if the control has to be on some flags or some very inputs from your IO devices, that you can mention by some code over here. So if it's unconditional jump, then you can make C equal to 00, some coding you can give, then it will not check anything but just directly jump to from this instruction. Similarly, if you do not want to have any jump in this case, so you can have some these as XXX and this will be some arbitrary encoding like 000 and 000. In such case, it will directly go to this one without having to think about it. So, basically this microprogram actually has one part of the address which is one part of the memory which is actually called, or in a row basically in a memory word, one part will generate your control signal, one part will be basically for the control select, that is depending on what you have to take the decision, and one will be actually the branch address field. So, basically there are 3 parts. So, we will take some elaborate examples which will actually clear out the whole theory for you. This is the figure which will actually clear what I was saying. We have to take it in slightly elaborate manner and let us look at it, what happens. We basically have a memory. So, we have actually 3 fields. So, this is the control function field. So, this is very, very important. The control signals are like program counter in, program counter out, all these things will be there basically. That is the main part of it. There are 2 other parts basically. One is called the condition select and one is the branch address field. Branch address field means it says that from this instruction, if some conditions are true or something, then the next address may be say 101. So, this is going to say that I am not going to, maybe at this present time in the instruction called say 001. So, I will go to 101 if some condition is true, that is what it is saying, and where I have to go? I have to go to 101. So, here you are telling which are the signals, here you are telling which is the which instruction location you have to go, and you are saying that what is basically the condition which has to be met. Now, how can I tell that I have to go to this branch? This is very simple. 101 means you have to update the value of microprogram counter, microprogram PC to 101. Otherwise, it will become from 001 to it will 010, it will increment. But you are telling, no, I do not want to go to 010, rather I want to go to 101 which is basically 5. So, if you look at it, so this part of the control signals will directly go to the ALU, the PC in and all these ports, but basically the branch address field is going to be basically one input to the MPC. So, if you allow or if the jump condition is true, basically the MPC will directly take the value of 101, that is what is going to take. So, this jump address is basically you are feeding as one input to the microprogram counter. So, now let us look at how the microprogram is designed. One is a reset field. Obviously, if you want to start from some 0 location, you can reset it, and this is what is the microprogram and the jump address. Basically, this input corresponds to the jump address which will load the microprogram counter to the jump address. But here you see, this is very interesting. There is a control to MPC. So, what is the control to MPC? One is load and increment bar. That means, if this line is 1, so what it is going to do? It is going to load the value which is available at this port. So, that means, if this is 1, you are going to take the value of 101 in the microprogram control and you are going to jump to 101. But if this line is 0, then actually what is going to happen? It is just going to make it as +1. So, basically it was 001. So, if this line is 0, you will go to 010 and you will be incrementing. So, the logic is very interesting. So, how the implementation is very interesting. So, you see the branch address field is actually feeding to the microprogram counter, and if this control is 1, then you are going to jump, and if this control line is going to be 0, then you are just going to increment basically. Now, who tells that this line will be 0 and 1, then my job will be done. How to decide that whether this line will be 0 and 1? That is going to be decided by this condition select field. So, for that they are actually having a multiplexer based implementation. You can have any other implementation, they have a microprogram based implementation. So, they actually say that, say for example, I have only 4 condition codes. So, you have a 4:2 multiplexer, as simple as that. If you have many conditions to be checked, that is going to increase. So, I say that there is actually only 4 conditions which has to check. And here I say that if I put if I put the value of code 11, so if I put 11 in the multiplexer, then of course this line is going to be connected to this. This I am making a default 0. That means if the condition select is 11, then this is 0. So, this part is connected to this, I am putting a default 0 over here, then this line is going to be 0 and I am going to just increment the microprogram counter. That means what? That means very interesting, that if I put the selection code 11, then the last part, the last bit of the multiplexer is connected to the MPC control and this is hard coded to 0. So, if I give the condition as 11, you are always going to get 0 and the microprogram will be just incremented. That means if I give the condition code as 1 1, then whatever in the branch address I need not bother, always there will be an increment in the microprogram. So it will go from 2, 3, 4, 5 like that, there will be no jumps. But say for example, I want to check if I want to go to 101 location if there is a control flag which is 1. Say this is the input 1, that is the carry flag. Say input 1 is connected to the carry flag. Now I will give the condition here as 0 1. So if it is 0 1, the second bit will be actually connected from here to here. The second bit is going to connect from the input control to the line over here. Now I am giving the control 1. So now actually this line is going to be 0 and 1 will totally depend on the totally depend on the condition that which is connected to this. So here I have connected carry 0. So if I put the 0 1, then this line will be 1 if and only if carry bit equal to 1, and this line is going to be a 0 if the carry bit equal to 0. So that means what? If I put selection condition as 0 1 and if the carry bit is a 1, so you are going to load 1 0 1. I put a 0 1 and if the carry bit is a 0, you are just going to have a 0 over here, and it means it will go to just an increment mode, it will actually execute the instruction number 2. So that is how actually it happens. And of course, if you want to go for jump unconditional, then somehow irrespective of this basically if I want to have basically a jump unconditional, that means I just want a 1 over here and whatever address I put, I should go over there. That means here the condition should not matter anything, or whatever condition I put over here should not matter anything. So I will put the condition as 0 0, which is the default condition in which is a jump unconditional. So if I put 0 0, the first bit of the multiplexer will be connected to the output, and here I have put a default 1. So in that case this line is always going to 1 and you are by default jump to 1 0 1, which is specified over here. So this is how actually it is implemented. So nicely looking at it, you will find the interesting stuff over here. So you are going to see that first bit is a 1. So if I put 0 0, this 1 is going to be 1, and whatever is the value in address field will come over here and you are going to jump to that instruction. Last bit I am always explicitly keeping as 0, that means if I put over here over condition 1 1, then this is going to be selected, this line is always going to be 0 and you are just going to increment. So that means if I put a 1 1, this branch address basically has no meaning, and if I put a 1 1, then no condition has, if I put a 1 1 over here, the branch address has no meaning because it is just going to be incremented. But if I say that if I put 0 0 over here, so in that case it is a jump is very very important. Here actually you are going to take 1 0 1 or wherever you want to jump, that becomes very important because this is going to be connected over here, but only thing is that no condition bits are required, you directly jump to 1 0 1. So this one corresponds to basically unconditional jump, this one corresponds to just increment. So in case of increment this has no value, but for the two other conditions like 0 1 and 1 0, some conditions will be checked. So how do I give input to the conditions? This I connect to carry input and this I connect to say maybe parity input. So and then if I put 0 1, then you will jump to the instruction only if there is a carry, and if I put 1 0 as the control condition select, then you will tell that if and only if parity bit is set, then I will jump to instruction 1 0 1. So therefore we have seen how this circuit basically implements the sequencing using a memory, because you have to remember that unlike FSM you do not have some flexibility like this where some condition checks are here and you go from this state to this state based on some condition, and control from going to here or going to here is done by state encoding. That is not possible. So we are actually implementing it in this nice interesting digital design fashion. So this is basically the organization of a microprogram control unit. So basically whatever I have told you is actually written in the slide. So to implement this logic we actually use this a multiplexer. So the multiplexer corresponds to jump unconditional, jump conditional and just increment. Basically that is what is the case. So if it is a jump on 0, so some 0 flag has to be checked. So that means if you have to so if you have some instruction like jump on 0 to say 1 0 1, so this one may be you have to connect it to the 0 flag. So if it is a 0, so this one will be a 1, it will be loading the instruction 1. So therefore means it has to be set. So how it is done, if the 0 flag is not set, multiplexer is 0, so it does increments the MPC whatever I have told you. So whatever I told you is explained in the thesis, I explained in the slide, you can just go through this. Now example. So much theory we have told and we have explained all these terms in case of a very abstract English, that if this happens you jump over there, this is a microprogram control, a memory is divided into some control signals, this part has to be for conditions, this part has to be jump address and so forth. So many things we have discussed. Now we will take an example and we are going to do it. Say for, as I already told you, say add R1, R2. So this is the instruction which is to be executed, that is the macro instruction. So you already know that instruction is to be first fetched and then decoded and executed. So as I already told you, so if so many times we have dealt with this, this is the microprogram or control 3 micro instructions which corresponds to fetch. So this one actually takes the value of program counter out to the memory address, you read the memory address, you basically select 0, add and z mean, that is you are incrementing the value of PC, then the incremented value of PC. By the way, we are actually all assuming a single bus architecture, then the output of program counter will go to Z, sorry, the Z will feed the program counter, Z is having the value of PC plus constraint, then you wait for some amount of time and then basically you dump the value of memory data register to the instruction register. So the instruction add R1, R2 comes to instruction register. So this is many times we have discussed it, and for almost all instructions, these are the 3 micro instructions required to fetch it. So let us see how the, so whenever you have to execute this instruction, automatically, say for example the program counter is fetching it. So immediately what it will do, the program counter will MPC will load, basically it will be loaded with a microprogram memory. So let us assume that is a microprogram memory, say it will go to 0, 0, 0, 1 and 1, 0. So it will immediately make MPC equal to 0, 0, which corresponds to the starting micro instruction for fetch, that is this one. So whenever any instruction has to be executed, it will make the MPC 0, 0. That means here we are assuming that the microprogram which corresponds to fetch of any instruction basically exists in this micro instruction memory 0, 0. So that is default. So after this is fetching is done, then we will see what happens basically. So we are assuming that the control function is 16 bits, that means we assume that there are 16 signals. In fact, we are not, something may be vacant, because as I told you, address widths are generally 2 bit, 4 bit, 8 bit, 16 bit, 32 bit and so forth, but the control instructions or the control bits may not be 2 to the power. It may be, because you might have 10 control bits like PC in, PC out, MAR in. So that may not be in the terms of powers of 2, because that corresponds to some basic hardware points in the circuit. So here they are taking 16, but the control signals are basically how much? 12 basically. 12, and they have kept 2 bits for condition select and 2 bits is for the address, because there are 3, basically in this case there are basically 3 memory words in this MPC, in the microprogram memory. So address field can be 2 bits, control they are keeping 2 bits, that bits they are assuming that control can depends only on 2 bits, that is 2:4 multiplexer, like that. Okay, so now let us see what. And we all know that in the first cycle, PC out should be 1, MAR should be in, read should be 1, select should be 0, add should be 1 and Z in should be 1. That is, these are the different points you have to set it. So it is very easy here, unlike a FSM. For FSM you have to design a circuit and synthesize it. Here you just write the first bit corresponds to PC, second bit corresponds to PC in, the first one corresponds to PC out, this corresponds to PC in, this corresponds to MAR in, read. That means what? This memory location will be read from the microprogram memory, it will go to this microprogram memory data register, and this point actually will be connected to the program counter in. This memory data bus, microprogram memory data bus will be connected to the PC in port. This will be connected to the MAR in port. This will be connected to the read port of the main memory and so forth. So just this will be coming out of the main microprogram memory data bus, that is the data register or the buffer register, and these points of the address bus is directly connected to the corresponding positions in the hardware block. And so it is very simple that the memory data is coming from the memory and it is directly connected to the different points and the job is done. So in the first thing, this cycle you know PC1 equal to 1, so I will store a 1 over here, PC out is 0, all other signals which are not mentioned over here are basically 0, MAR in, so I will put a 1 over here, read I will put a 1 over here, select 0 over here, already told, so I am putting it, add is to be 1, Z in to be 1, and of course all other signals here are basically 0, because I do not require them, so basically put it as a default to be 0. So see Z out equal to 0, this corresponds to some other 0, MDR out is 0, IR in is 0, WFMC is 0, and all other values you have to put it 0. So, only whatever are mentioned over here you put it 1 and 0 as explicitly told. Explicitly it is telling that select has to be 0 because program counter has to be incremented by a constant, that you explicitly put as select as 0, and whatever mentioned over you put 1, and all others has to be reset to 0, that is done. So, whenever MPC will point to here, so these values will be brought from the main microprogram memory data bus, and it will go to PC out 1, PC in, this will go to PC out 1, PC in, PC out is going to be 1, sorry, PC in is will be 0, I will not do anything with it, MAR will be 1, so all the connections will be done, the values will be opened, done, and your job is done. Next, because in this case there is no question, again I will show you, this is actually corresponding to the branch and control select. So, in this case first I am putting at 1 1. So, if you look at what was 1 1, 1 1 is basically corresponding to this bit, that means basically it is going to give a 0 over here. So, it is just incremented. So, if you look at it, I am putting this one and branch and stress is 0 0. That means basically I can write it over here for your ease. So, here I am doing it as XX and control bit is 1 1. So, control again I will write it, that is better for us. So, when I am said that is this control is basically 1 1, that means I am not going to look at this next this is next address, I am not going to look at the next address anyway, because the control is 1 1 means whatever be the control means input, I will just increment the value. So, I put 1 1 here and your job is done. So, automatically MPC will become 2, it will be just incremented because 1 1 as I have showed here corresponds to increment and not load it to any variable next location. Next what? Next you see Z out, PC in and WFMC. So, in this case PC in will be a 1 and basically Z out will be a 1 and WFMC is a 1. WFMC 1 means basically it is a signal which is generated, and that means you are waiting for another signal from the memory which has to come. If both of them comes, then only you can go to the next one. So, there is a slight hardware block over here which I am not describing. So, WFMC means it has generated a signal which is called wait for the memory. Memory said that I am ready, you can read my data. When both the signals will come, then automatically it will trigger and you are going to the basically the next instruction. So, this part you can take as a black box, that unless this WFMC actually ensures that unless another same similar acknowledgement comes from the memory that the data is ready and it has been put to the memory data register, you can take the value, basically you are not going to go to the counter number 3. So, there is a hardware block for that, you need not put too much mind about it, just assume that it happens. Now what? Now here also condition check is 1 1, that means here also there is no question of any kind of branch, you just wait, and in this case basically it is XX. So, no nothing to whatever even if I put 0 0 1 1 or 1 0 whatever here, but it is not going to jump to that place because conditions are 1 1, that is default increment. Now, we will come to memory location 3. So, memory location 3 says that MDR out because already memory has been fetched and you are going to dump it to the IR. So, in this case you are going to have MDR out equal to 1 and IR in is equal to 1, and then it is basically here. After that this actually next program next part will be halt or end, and then your microprogram count. The next I have not shown over here. So, when it will come over here, it will correspond to end, and then MPC will not increase, it will actually microprogram PC after 3 basically it stops. We can also put some condition for stop over here in the next page, it will not get incremented to 4, rather it will actually be floating. Now, what happens basically the instruction register, now the value has come to the instruction register, it will decode what is the instruction. If it is an add instruction, then MPC will correspondingly point to some other portion of the main microprogram memory which corresponds to such a code which corresponds to add. If it is a load instruction, IR will decode it and basically it will point to some other memory location, some other microprogram memory which looks like this, and what is going to happen, that will have the corresponding signals which will correspond to what? Which will correspond to basically the microinstruction sequence for load instruction, and that way basically it will happen. So, as we were looking at basically this microprogram control, so one thing you might have observed that whenever actually these control signals are coming from each of these memory words in the microprogram control memory, you can see that simultaneously you are controlling each port or each point you have to control in one go or in parallel. That is, if you want to make PC out equal to 1, you are setting it as 1. In the same time instant you want to make read equal to 1, you can make it as a 1, and all we are doing in a very parallel fashion. But if you look, this matrix is basically a very sparse matrix. Like in the second time instance, you only require 2 signals to be 1, and in the third you just require 2 signals to be 1. So what happens basically, there is a lot of wastage of memory when you are talking about the microprogram control memory, where you are feeding in the signals required to be made 0 and 1 at each time instance of the microprogram. So this actually method is called a horizontal method, and in which case you simultaneously control as many signals as possible. How it is possible? Basically you have a memory in the microprogram control memory, and you put zeros and ones as required, and each bit of the memory word corresponds to one port. So you parallelly send all the signals to all the ports to be controlled, and it is very fast. But the problem is that as many ports are there, that much long your word has to be. So if there are some 32 points to be controlled, the word has to be 32, and so forth. But on the contrary, if you see, you see lot of zeros. So that means actually this is very sparse in content. So if you have such sparse content, then you are wasting lot of memory. So how can we actually implement in a better way? So but there are several advantages, like in one go you can control all the control signals required to be given at an instance of time. So it is parallel, it is fast, there is no processing involved. Like an FSM, you need to find out at each state what is the control signal required. So you have a circuit which generates the signals from that state encoding and so forth. So that is slightly complicated in terms of circuit, but here it is very simple. Whatever you want to give written in the memory, just apply it. But there is lot of wastage because of sparse. So therefore, this sparse can be utilized to optimize basically. That means somehow you can, if you can somehow throw away these sparse values, like wherever it is 0, you do not require them, only you keep the ones in some way, so that the whole memory can be optimized. So that actually is called a vertical microprogram. So in vertical microprogram, the microinstructions are kept rather short by 2 basic techniques, and we will see about the techniques basically. So what are the 2 techniques? One is as we will see, there are the 2 broad techniques, one is a hybrid technique and one is absolute vertical technique. So whenever we want to optimize based on encoding or compressing of the signals in each of the cells or each of the words in the program control memory, we call it as a vertical microprogram. In horizontal, it is very flat and no optimization is there. So now what way you can do? The only way you can do is you have to encode it by way x, y, z. So whenever you want to optimize on sparse values of a matrix, there is only one way to do it, you have to encode it. Now encode can be very flat, like if there are 16 bits as output, you go for a 4:16 decoder. That is the one way of compressing them. There can be several others as we will look here. So basically first, the most formal or the preliminary way of doing it is basically encode the signals in the control memory. So what you do? So whatever signals has to be applied, you just encode them and use a decoder. I will show you a figure and then we will come back. So for example, this is one word of the control memory, or this is the format of the control memory word. So PC in, PC out, MDR in, MDR out, all these values are there. Now I encode it. So how many are there? There are 8 bits which has to be controlled, or 8 locations which has to control. So I just put a 3:8 decoder. Then what will be the memory size? The memory size will be 3 bits. So if you give 0, 0, 0, the corresponding row of the decoder will be 1 and you generate PC in equal to 1. Next, if you give the signal 0, 0, 1, this is the memory. So memory is now 3 bit. So if you give the value of 0, 0, 1, 0, 0, 1 in the memory, so you are going to make the second line high of the decoder and you are going to get the value of 0, 0, 1, which actually makes this line high. So in fact PC out will be equal to 1. So now you have to observe that this is one of the drastic way of compressing. So instead of 2 to the power n, the size will just become n, or if it is n, you will go for log n upper ceiling. So it is 8, you are going to get 3, highly compressed value will have. But the problem is that at any point of time, only one of these signals can be made 1. So now the things will start becoming slower. Say for example, generally we know that what happens basically, we always have program counter out and memory address register in. So this actually always happens simultaneously. So here what will happen? First you will have to give the value called 0, 0, 1. So if you are giving the value 0, 0, 1, PC out will be equal to 1. But now simultaneously you cannot also make MAR in equal to 1. So what you have to do? It will be in 2 steps. In first step, the memory control memory will give the value 1, 0, 0, 1, which will make PC out equal to 1. Then the program counter, so there will be some stable register or 1 bit flop which will hold the value, that it has to be a 1. Next step what you do? Next step you give the value of 6, that is MAR in, you have to give the value 100 in the control memory. That means you are going to, this value will be fed from the control memory to the decoder. So now it will make MAR in equal to 1. This is say T1 and this is say T2. Then what is going to happen in 2 time steps, this configuration will be there, PC program counter output will go to the memory address in. Now what happens? Now but still now PC out is also equal to 1, this is also equal to 1. Now you have to give a time step where you reset actually both. In case of a horizontal microprogram, you need not worry about resetting it or holding the value. Simultaneously you give this as 1 and this as 1 and your job is done. But here as we are compressing it, we are calling it a vertical microprogram because we are compressing the structure of the memory. So you can only make any 1.1 at a time. So I make PC1 equal to 1 at a time 1. Then in the next time go, if I make MAR equal to 1, in that case there should be some guy to remember that PC out was equal to 1 at that point of time. Because otherwise what is going to happen, when I am making this as 1, this line will become a 0. Because whenever I am giving the signal 110, basically PC out will become 1. So here there are 2 disadvantages. One is that you will have more number of steps required to give simultaneous ones to the different control positions. So here 2 ones were required, so you require 2. If multiple ones are required, you have that many number of time steps. Not only that, whatever was 1 simultaneously required in a horizontal microprogram, those values you have to remember, like PC out equal to 1 and MAR equal to 1, together they should be 1, but here you are doing in 2 steps. So somehow the program counter out has to be 1, has to be remembered till you go to the second step, and after the second step is done, then again you have to reset this both and then again start from the third location and so forth. So that is like, these are the 2 disadvantages, longer time you have to remember and again you have to reset. But the advantage is that the memory size actually gets compressed in the value of, in the terms of log, from 2 to the power n it will go to the order of to n. So that is a big advantage. So if you have lot of zeros, then such problems will become, in such some kinds of number of stages will be less. But if you have more number of ones, then making them simultaneously 1 is not possible, so the time steps will increase. But this vertical microprogram advantage comes because there are lots of zeros and therefore only we go for the vertical technique. So it is also slower compared to a horizontal microprogram, right? So now we go to the theory. So what it says that it encodes the signal, as I have shown you. The output, the control signals are stored in an encoded format in the control function field. The outputs of the control function field are first given to a decoder and then they are applied to the ports. As we are having a decoder, so only 1 bit can be 1 at a time of the output of the decoder, so only 1 control point can be a 1. And the control signals are divided into more number of control steps, obviously, because at each point of time only 1 bit can be a 1, so more number of control steps will be required. Vertical optimization requires several micro instruction executions to do when one horizontal instruction can do it. That means in vertical approach you require more number of micro instructions, in horizontal a very less number of will do, because horizontal is parallel approach and vertical is a sequential approach of solving the problem. Now that is one way of solving, that is just optimize, just full optimization, full vertical, just encode it by a technique which you have shown. You require a decoder to solve it. But now there is another way, as I told there are 2 techniques, another way is very interesting, that can I make a cluster. So what is the cluster idea? I will take a figure and then I will come back to the theory. So these are cluster. So we are clustering. Now we will not make full compression. What we will say that we will try to find out which signals are simultaneously required to be 1. Like as I told you, PC in and MAR, PC out basically always requires to feed memory address register in. That is generally we have observed. So what I do, I actually make a cluster, 2 clusters. In one cluster I will put the PC out, in another cluster actually I will put memory address register in. So if there are 2 different clusters basically, so interestingly what is going to happen, I can make this one and this one also simultaneously. But as there are 2 different clusters, means this is one control memory and this is another control memory. Now there are 2 clusters, I mean we should not call it 2 different memory, basically logically we have partitioned into 2 different memory clusters. So in this cluster only 1 bit can be made 1 and in this cluster also 1 bit can be made 1. But simultaneously 1 bit can be 1 here and 1 bit can be 1 here. So that parallelism I have given. So this is actually called a hybrid kind of a multi-programming approach. Neither it is fully horizontal, neither it is fully vertical. So here what they have done, they have made a cluster, in which case if you look, they have made a cluster of PC in, PC out, MAR in, MAR out 1. Generally if you see, we always try to put in and out of a port in one cluster, because generally PC in and PC out do not want to make it one simultaneously. Similarly, a memory address register, memory data register in and memory data register out together you do not require to be in, but generally we can have memory data register out and instruction register in simultaneously. So this one I can make one and this one I can make together. Similarly, program counter out generally goes over here. So that way we can make a cluster thinking out that which of the 2 bits can be simultaneously one, that you put in different clusters and your job is done. So but if I do it like this, so you can see the hardware requirement is slightly higher. In the previous case we required a 8:3 decoder, but here you require 4:2 decoder. So 2:4 decoder, side area higher side. The memory number of bits were 3 in this case, but now it will be 4 bits in this case. But this will be slightly faster compared to the full vertical case, because simultaneously I can take one signal here and one signal here and I can make one at a time. So if you make full horizontal, that if you want to make only one bit in one cluster, that is one extreme, which is called the horizontal, and here if you think everything is in one cluster, that is another extreme, that is called the fully vertical microprogram. So in this case this is something called a hybrid. So the basic guideline is you choose the signals which very frequently has to be ones, so that you put in separate clusters. So here I have given an example of 2 clusters. You can make multiple clusters depending on the needs. The motivation is in each cluster you should not put signals which requires to be one simultaneously, but it may not be easily solvable, because if you go to that level that we are keeping individual bits in a cluster which can never be one together, then you will go to a fully horizontal microprogram where each bit is independent. So we can try to think that in very high number of micro instructions which signals are to be one at in one point of time, you get to give it to a different clusters like PC out and memory address register in. This will always happen in the microprogram instructions corresponding to fetch of an instruction. So you put it to a different clusters. So that is basically the idea. But sometimes if you say that the program counter in, maybe you have to go to, for example, I can say that somehow for some reason, maybe say that program counter out has to go to memory data register in. That is a stray example. Then of course you require 2 bits. For example, if you also I am saying that here there is another cluster which is having say R0 in, that is some R0 register is also in this cluster. So just an example. So in this case basically the memory data out and R data register in will not happen. For that you will require 2 steps. So that the cluster that means whatever is in one cluster, if you want 2 signals to be one simultaneously, they has to be done in 2 steps. That cannot be done in a single stage. In that case the time step will increase, but in between large number of clusters are there. For inter-cluster multiple bits can be one simultaneously. So this way of compressing is actually called a hybrid approach, and sometimes we call hybrid kind of a vertical organization. So basically that is what is the idea. So another technique basically is to be made clusters. So in each cluster signals which did not be one simultaneously in one step you put in one cluster, and whichever need to be one simultaneously you put in different clusters. For example, like PC out and memory in should be made simultaneously. Similarly, what I was telling in the example is written in this slide. You can go through the slides basically. So now if you look at a comparison, so in this case basically there is a basically what idea in this example, there are 8 bits that if you look at this slide, so means how to make a control etc, all the comparisons are set. So in this example there are 8 bits in the control field, so you require a decoder to solve the problem. For example, if PC in is to be made 1, then the values of the control field 0 0 0 and decoder will make it as a 1. So it actually this slide actually is the interpretation of the figure. This interpretation of this figure is given in this slide, and I have already explained you. This is just for you to read and get what I was actually discussing. But disadvantage is that more than one control point cannot be made in a step if it is a full vertical arrangement. This actually this slide actually explains this figure. This is what I have described, that how to do an intercluster organization. So now consolidating what we have discussed, in horizontal microprogram less number of micro instructions are required. It is a fully parallel architecture, no encoding, so extremely fast, but actually wide control field is required, so the memory size will be higher, and there will be, because there are lots of zeros involved generally, because only 1 or 2 points need to be controlled simultaneously, that is made 1, so there is loss of memory wastage. In vertical what we do, actually we are encoding the control units, control signals, so there is a less number of memory is required, so wastage is less, but you require decoding and encoding, so leading it to slower speed. And not only because of decoding, you require multiple number of steps to solve the same control problem, so it is a long time taking approach. And what we have also seen that there is some kind of a hybrid approach in which you can make nice clustering based on the fact that two signals which has to be 1 should be given to different clusters, then you get something, a good trade off, that without wasting much memory you get a almost near speed up as a fully horizontal microprogram. So basically with this we come to the end of this unit. In the next unit basically we will look in more depth, basically that type, depending on different type of instructions, macro instruction, how exactly the full instruction will basically go through the micro instructions and how they will be executed, because mostly in this unit we have tried to focus on the fetch part. But after fetching actually there is a instruction decoding, and depending on the type of instruction, whether it is an add or subtract or something, you have to go to different location from where the corresponding micro instructions are there. That is how a full instruction can be executed. So all those components will be looking in the next unit. This unit actually gave you an idea that what is a basic microprogram architecture, how you can optimize, what are the basic microprogram in memory looks like, what is the microprogram counter, the basic idea we have given. In the next unit actually we will try to go in slightly more depth with the concepts and try to see basically main idea will be how we can basically take a full code and try to see the full execution in terms of micro instructions. That is, we will try to go in elaborate more on some of the points which we have, the basics which we have discussed in this unit. So before we end, as we always discuss some questions and try to see if the objectives are met. So the first question is, what is a microprogram control unit, what is the basic idea of working, how a machine instruction is implemented in terms of microprogram. So after discussing this unit, I think you will be able to answer this, and once it is answered, basically this comprehension objective that explains the concept of microinstruction and basically construct the basic components, because how a machine instruction is implemented in terms of a microprogram, so the basic architecture etc. So this comprehension and this construct synthesis objective will be made, because you will be describing a basic architecture. You should be able to basically describe the basic architecture of a microprogram control unit which we have shown, and then just you take how a code actually gets broken down into some terms of some signals, the basic theories. So this actually fulfills this objective. The second question is, I ask you that you take a instruction add R1 and R2 and you take a control memory 16 bits signals, condition bit is 2 bits and address bit is 5 bits. That means the address space is now 2 to the power 32. I ask you to that you please try to see how the full instruction can be executed, because mainly in this unit we have discussed the fetch part of it. After fetch, if it is an add, some other set of micro instructions will be addressed. If it is load, some other set will be executed. That is, the fetch part is common, but after that it gets is bifurcated depending on the type of instruction. So now please try to because already we have discussed how to do for the fetch, please try to extend it for add and basically see how the microprogram memory looks like. And of course we saw that 3 memory locations are required for fetch, but as I have asked you to go for the other steps also, that is executing the instruction, so we require a higher memory size. So I have kept the address bit field as 5, so that you have the places to put the other signals which will be required for exact execution of the add R1 and R2, which basically comes after the instruction is decoded. So that part you can try. So this actually questions will directly help you in meeting this objective, that construct the basic components of a microprogram control unit and its organization, because here we will have the fetch stage as well as you have the decoding and the execution stage also. In fact, again you will be able to categorize the control signals in terms of groups and format of the micro instruction, because in this case we will have basically 2 basic parts will be there, one is for the fetch and the other part is for the execution. So you will be able to categorize. Also if you want to try with add, then also you can try with load R1 memory. If you try these 2 basically, then you will be able to find out how I can categorize the control signals based on the different format of micro instructions for different kind of codes etc. So by these 2 questions actually you will be easily able to, you should be able to solve these questions based on the discussion in this unit, and actually you meet these objectives which was the target of this unit. With this we come to the end of this unit. Thank you.